Welcome to this video lecture. Myself Atul Kumar, working as an assistant professor in Department of Computer Science, Rajiv Gandhi Memorial, Government College, Jogindarnagar. In this video lecture, I will discuss about various arithmetic and logic micro operations in computer architecture. So, what is micro operation? Micro operation is a basic or elementary operation performed by a basic computer. So there are different kind of basic micro operations that are performed by a basic computer. These include addition, subtraction, increment, decrement, and shift micro operation. So these are a table, various arithmetic micro operations shown in the table. The first operation is R3 equal to R1 plus R2. This one is a symbolic representation on the left hand side, and right hand side is the description of these micro operation. So here in the first micro operation, the content of R1 and R2 is added, and the result is transferred to R3. In the second micro operation is R3 is equal to R1 minus R2. So the content of R1 minus R2 transferred to R3. In the third micro operation, R2 is equal to R2 var, that is the complement the contents of R2. And the fourth micro operation is R2 equal to R2 var plus 1. So it is basically the 2's complement of the content of R2. The next micro operation is R3 is equal to R1 plus R2 var plus 1. So it implies R1 is added to the 2's complement of R2, and the result is transferred to the register R3. Next is the R1 is equal to R1 plus 1, that is the increment operation, and it increment the content of 1 by 1. Next is R1 is equal to R1 minus 1, it decrements the content of R1 by 1. So these micro operations are implemented either with combinational circuit or with the help of binary up down counter. The arithmetic operations of multiply and divide are not shown in the table. These two micro operations are valid micro operations but are not included in the basic set of micro operations. So in addition micro operation, as I have discussed, it adds the content of R1 and R2, and the result is transferred to R3. So these are two registers R1 and R2, and there is a NOT gate inside this, and the result is 111. When it is supplied to parallel binary adder circuit, then the result is R3, that is the sum of two registers R1 and R2. Similarly, we implement subtraction micro operation through complementation and addition. Increment micro operation is implemented with the help of combinational circuit or with the help of binary up down counter. Decrement micro operation is implemented with combinational circuit or with binary up down counter. So this one is the basic arithmetic circuit. It for the implementation of micro operations, arithmetic micro operation. So in this circuit it includes 4 multiplexers, each of 4 into 1, that it takes 4 inputs and produces 1 output. There are 4 full adders, these, and the outputs generated by these full adders is D0, D1, D2 and D3. There is also a carry in. There is also a S1 and S2 selection lines, S1 and S2. Based on these selection lines, the input is selected. There is also the inputs A and B, and so A0 is given to multiplexer 0 to the line 0, A1 is given to the line 1, and so on. Uh, so the arithmetic micro operation listed in table can be implemented with one of the arithmetic circuit as shown in this figure. The basic component of arithmetic circuit is the parallel adder. It has four adder circuits that constitute the 4-bit adder and four multiplexers I have discussed for choosing different operations. There are 4-bit inputs A and B as shown here in the circuit, and 4-bit output D. The four inputs from A go directly to the X input of the binary adder. Each of the four inputs from the B are connected to the data inputs of the multiplexer. So A are connected to binary adders and B is directly given to the multiplexer. Like you can see here, A is given to the adder, full adder, A1 is given to this full adder, A2 is given to this full adder. So A is given to the full adder and B is connected to the multiplexer. So the input B is connected to the multiplexer and input A is connected to the full adder. So each of the four inputs from B are connected to the data inputs of the multiplexer. The multiplexer's data input also receive the complement of B. The two other data inputs are connected to logic 0 and logic 1 as shown in the diagram. This one is a logic 0 and this one is a logic 1. The two other inputs are connected to these two logics. The four multiplexers are controlled by two selection lines, as I have shown you the selection lines S1 and S0. The input carry Cin goes to the carry input of full adder in the least significant position. The other carries are connected from one stage to the next stage. So this one is the basic arithmetic circuit function table based on the selection lines S1 and S0 and Cin and input Y, the output is predicted. So when S1 is 0, S0 is 0 and Cin 0 and B is applied as an input Y, then the output is D is equal to A plus B, and this one is the add micro operation or addition micro operation. The next is when S1 is 0, S0 is 0 and Cin 1 and input Y is B, then D is equal to A plus B plus 1. This means add with carry micro operation is performed. The next arithmetic selection line is S1 is 0, S0 is 0, Cin 0, then and B bar is the input given to Y, then D is equal to A plus B bar, that is the subtraction operation. The next is 0 as S1, S0 as S0 as 1 and Cin as 1 and B bar is equal to Y, then D is equal to A plus B bar plus 1. This is a subtraction operation. Next is equal to when S1 is equal to 1, S0 is 0 and Cin 0 and input Y is equal to 0, then D is equal to A. This means a transfer micro operation of A. Next is S1 is equal to 1, S0 is 0 and Cin is equal to 1 and input Y is equal to 0, then D is equal to A plus B. This means it is a increment A operation, increment of A. Next is S1 is equal to 1, S0 is equal to 1, Cin is equal to 0, then input Y is equal to 1. This means D is equal to A minus 1 and it is a decrement of A. Next is S1 is equal to 1, S0 is equal to 1, Cin is equal to 1 and input Y is equal to 1. Then the output is D is equal to A. This means transfer the contents of A. So this one is the theory about this. When S1 is S1 and S2 both are 0, the value of B is applied to the by inputs of adder. If Cin is equal to 0, then output is equal to addition operation D is equal to A plus B. When S1 and S0 is equal to 0 and 1, the complement of B is applied to Y inputs of the adder, and if C in is equal to 1, then D is equal to A plus B bar plus 1. This is the subtraction of A minus B, is a subtraction micro operation. Third is when S1 is and S0 is equal to 1 and S0 is equal to 0, then the inputs from B are neglected, and instead of all the zeros are inserted into the by inputs, the output becomes D is equal to A plus 0 plus C in, and this gives D is equal to A. When S1 and S0 is equal to 1 and 1, all the 0 are inserted into the Y inputs of adder to produce the decrement operation D is equal to A minus 1 when C in is equal to 0. Next, we have a logic micro operation. So logic micro operation specify the binary operations for strings of bits stored in the registers. So basic micro operations used in logic micro operation involves OR gate and complement and exclusive OR. So there are 16 different logic micro operations that are performed with the help of two binary variable x and y. So in the next table that I will show you, there are 16 columns starting from F0 to F15 represent a truth table of one possible Boolean function for the two variables x and y. So these are the truth table for 16 function. Based on the input value, the function f0, f1, f2 up to f15 are selected, and we create these 16 Boolean functions of two variables x and y are expressed in the algebraic form as shown below. When f0 is equal to 0, this means that all the content of f0 is 0. So this one is the micro operation f is equal to 0 for first function f0. The next is the micro operation when both input is 0, the output is 0. When one of the input is 0, then output is also 0. This means this one is a meaning a AND operation. So the output of f1 function is x dot y, that is a AND. Similarly, you can create a Boolean expressions for all the micro operations with the help of k maps, and these are the k maps for 16 Boolean micro operations functions. Like if we can see for this, suppose we have to create a Boolean expression for this. So the Boolean expression for this is x XOR by. Similarly, if we want to create a Boolean expression for this, here the common element is y, so f5 is y. We have to just see the common element and just create the Boolean expression. Here the common element is x dash, because x dash and y. So the expression for f4 is x dash and y. Here there is no common element, there is no 1, so f0 is equal to 0. For this there is the expression xy, and for f2 xy bar, for f3 x. Similarly, we have for f8 x bar y bar. For f9 we have a Boolean expression x exclusive or y and bar. For f10 we have y bar. For f11 x plus y bar. f12 we have x bar. f13 we have x bar plus y. f14 we have x bar plus y bar, and f15 we have 1. Thanks for watching this video lecture.